Welcome back to Refinery Pro. This is your host, Manoj Kumar. In today's episode, we are diving into episode 3 of our comprehensive series on refractory materials, and today's focus is on something absolutely critical: understanding refractory properties. Now, you might be wondering, why should I care about all these properties? Well, here is the thing: selecting the wrong refractory for your application is like choosing the wrong tool for a job. It simply would not work efficiently, and it can cost you a fortune in downtime and repairs. By the end of this episode, you will understand exactly which properties matter most for your specific refinery application. So, let's get started. Understanding refractory properties and their relative importance is absolutely fundamental to selecting the right material for your specific application. Here is a critical concept: not all properties are equally important in every situation. Let me give you some real-world examples. First scenario: in a furnace where your primary goal is heat conservation, thermal conductivity becomes your most critical property. You want a material that insulates effectively. Second scenario: consider a fluid catalytic cracking unit, the FCCU. Here, erosion resistance is the prime requirement. Because you've got hot catalyst particles racing through at high velocities. Here your focus will be material conservation, not the insulating properties. Third scenario: think about equipment downstream of an H2 reformer, like a PG boiler or cold collector. Here, refractory comes into direct contact with hydrogen gas. In this case, resistance to hydrogen becomes absolutely the most critical property you need to consider. This is why engineering judgment is so important. You can't just pick any refractory and expect it to work. You need to understand your operating environment first. Now that we understand why this topic is important, let us organize the landscape of refractory properties. Think of this as a framework with 3 major categories. Keeping this structure in mind will help you approach material selection in a systematic way. Category 1: General properties. These are the foundation. They describe the basic physical characteristics of the material. Examples include density, porosity, cold crushing strength, modulus of rupture, and chemical composition. In simple terms, these properties tell you what the material is made of and how strong it is at the most basic level. Category 2: High temperature properties. This category is critical because it shows how the material performs under actual working conditions. Here we look at refractoriness under load, creep behavior, hot modulus of rupture, thermal conductivity, thermal expansion, and linear shrinkage or expansion. These properties reveal how the material behaves when exposed to heat and stress in real operations. Category 3: Special properties. These are designed to address specific operating challenges. For example, erosion resistance is important in high-velocity environments. Carbon monoxide resistance matters in reducing atmospheres. Gas permeability is relevant for porous structures. Acid resistance protects against chemical attack. And thermal shock resistance ensures survival under sudden temperature changes. Each property is measured using a defined test standard and method. In the upcoming slides, we will explore how each property is tested, what the results mean for your application, and why they are significant in real refinery operations. Let us begin with density, one of the most fundamental general properties of refractory materials. Bulk density is calculated using a simple equation: total weight divided by total volume. At first glance, this seems straightforward, but the way we measure bulk density can make a big difference. There are 2 approaches: The first is direct measurement, which is fairly self-explanatory. The second, and more technically rigorous, is the direct volume determination method. In this method, the formula is expressed as B equals D divided by W minus S, where B is the bulk density in grams per cubic centimeter. D is the dry weight of the specimen in grams. W is the saturated weight. S is the suspended weight. So why does bulk density matter? Because it directly influences both thermal performance and mechanical strength. A denser refractory usually provides greater strength, but it also conducts more heat. A lighter, more porous material offers better insulation, but at the cost of reduced strength. It is always a trade-off. Understanding this relationship is essential for selecting the right refractory material for your specific application. Now let us talk about porosity, a property closely related to density, but measuring something very different. Density tells us the weight-to-volume ratio. Porosity tells us how much void space exists inside the material. To measure porosity, engineers often use the evacuation method, and there are two formulas you should know. The first formula is P equals W minus D divided by W minus S multiplied by 100, where P is the apparent porosity. W is the weight of the soaked specimen suspended in air. D is the dry weight of the specimen. S is the weight of the soaked specimen suspended in liquid. The second formula is P equals V1 divided by V multiplied by 100, where V1 is the volume of water absorbed. V is the total volume of the specimen. So why is porosity critical? Because it determines permeability, thermal properties, and resistance to gas or liquid penetration. In a reducing atmosphere, such as the carbon monoxide environment inside a blast furnace, high porosity becomes a liability. It allows gases to penetrate and weaken the refractory. But in insulation applications, controlled porosity is actually an advantage because it helps trap air and improve thermal efficiency. In short, porosity is the property that tells us whether a refractory will act as a barrier or a sponge. Understanding this balance is essential for choosing the right material for each operating condition. Let's talk about cold crushing strength, or CCS, a test that is widely used but often misunderstood. CCS measures the compressive strength of a refractory at room temperature. And here is the critical point: it does not directly tell us how the material will perform at high operating temperatures. In fact, it's quite rare for refractories to fail under cold, static loading. So why do we test it? CCS acts as an indirect indicator of several important properties like abrasion resistance, the degree of vitrification, burning temperature, and even material purity. In other words, it's a quality control checkpoint. For insulating bricks, CCS has a slightly different meaning. It's less about hot performance and more about mechanical strength during handling and transport. Imagine moving tons of insulation bricks across India from the factory to the refinery. If the bricks can't withstand shipping stress, they will never make it to service. So when you see CCS values on a data sheet, remember, they are telling you something about how the material was produced and its general robustness, but they are not a direct predictor of hot service performance. Now let's see how cold crushing strength, or CCS, is actually tested and measured according to ASTM standards. For bricks, the standard test specimen is a full-size brick, typically 9 inches by 4.5 inches by 3 inches, or sometimes 2.5 inches high. This is the industry benchmark. For castables, the specimen is different, a 50 mm by 50 mm by 50 mm cube. That's because castables have a different microstructure compared to fired bricks, so the test needs to match the material. At least 5 samples are tested using either a hydraulic or mechanical compression machine. Testing multiple samples helps account for variability in production. The CCS value is calculated using a simple formula. CCS is equal to load divided by area in kg per square centimeter. To give you a sense of typical values, a high-quality dense refractory brick might show 250 to 350 kilograms per square centimeter, while a high-performance castables can exceed 400 kilograms per square centimeter. CCS for insulating bricks are much lower, usually 20 to 50 kilograms per square centimeter, because their design prioritizes insulation over mechanical strength. So, CCS testing gives us a reliable measure of robustness and production quality, even though it doesn't directly predict hot service performance. Now, let's move from compression to bending strength. This is where the modulus of rupture, or MOR, comes in. Remember, CCS tests compressive strength under crushing forces, while MOR tests tensile and bending strength under a different loading scenario. Here's how the test works. A specimen of specified size is placed flat onto bearing cylinders with a span of 7 inches between them. Load is then applied at the midpoint. Essentially, we bend the specimen until it breaks. At least 5 samples are tested, each loaded at a controlled stress and strain rate. The test can be performed on either mechanical or hydraulic equipment. The formula for MOR is equal to 3WL divided by 2BD square in kg per square centimeter, where W is the concentrated load applied. L is the span between supports, 7 inches. B is the breadth or width of the specimen. D is the depth of the specimen. Specimen sizes vary depending on the standard. As per ASTM 733, it is 50 mm by 50 mm by 230 mm bar. As per Indian standard IS 10570, it is 40 mm by 40 mm by 160 mm bar. As per ISO 5014, it is 25 mm by 25 mm by 150 mm bar. So why is MOR important? Because many refractories face stress from thermal gradients and mechanical loading during service. A material with high CCS but low MOR can be brittle and prone to cracking under thermal shock. In short, MOR helps us understand how well a refractory can resist bending and cracking when exposed to real-world stresses. For dense refractory bricks, MOR values typically range between 40 to 60 kg per square centimeter. For high-performance castables, they can exceed 70 to 100 kg per square centimeter, while insulating bricks show much lower MOR values, usually around 5 to 15 kg per square centimeter. Now we are entering the realm of high-temperature properties. And this is where refractory performance truly matters. One of the most important tests in this category is called refractoriness under load, often abbreviated as RUL. This test measures how a refractory brick resists deformation and shear when it is subjected to both heat and compressive load. Conditions very similar to what happens inside a real furnace. According to the ASTM C16 test method, which is widely recognized internationally, at least 2 standard bricks are used, sized either 9 inch by 4.5 inch by 2.5 inches or 9 inch by 4.5 inch by 3 inches. Larger shapes can also be cut down to this standard size. A uniform compressive load of 25 pounds per square inch is applied to the stack of specimens, and the furnace heats the sample gradually, following the ASTM C16 procedure. This is not a simple constant temperature test. because only during the final 1.5 hours does the temperature approach a constant level, allowing the center of the brick to reach the same temperature as the surface. If the brick fails under shear, the temperature at that moment is recorded as the RUL temperature. If no shear occurs, the furnace is cooled down to 1000 degrees Celsius or lower before the load is removed, and the specimen is then cooled to room temperature, where any deformation is carefully measured and recorded. In short, the RUL test is critical because it tells us how a refractory will actually behave under the combined stresses of heat and mechanical load. It is the true measure of performance in service. Refractoriness under load, RUL, is expressed in terms of temperature in degrees Celsius at which a refractory specimen deforms under a specified compressive load. Typical RUL values vary widely depending on the type of refractory. Dense fire clay bricks often show RUL around 1350 to 1450 degrees Celsius. High lumina refractories can reach 1500 to 1700 degrees Celsius, while insulating bricks usually have much lower RUL, often below 1200 degrees Celsius. Now let us look at the ISO 1893 method, a different approach to measuring refractoriness under load or RUL. Unlike the ASTM C16 procedure, the ISO method evaluates refractory deformation under a constant load, while the temperature rises progressively. This is often referred to as the RUL differential method. The test can operate up to a maximum temperature of 1700 degrees Celsius, which is significantly higher than ASTM C16, making it especially valuable for ultra-high temperature applications. The specimen requirements are also different. Instead of rectangular bricks, the ISO method uses a cylindrical sample, 50 mm in diameter and 50 mm in height, with a coaxial hole running through its full height. This hole, 12 to 13 mm in diameter, serves as a precise reference for measuring deformation. The loading criteria are carefully defined. A load of 0.2 Newton per square millimeter is applied for dense refractory products, while a lower load of 0.05 Newton per square millimeter is used for insulating products. The reduced load reflects the different structural character of insulating materials. The temperature schedule is straightforward but strict. The sample is heated under a controlled program until either the maximum permitted temperature, typically 1700 degrees Celsius, is reached, or the subsidence, meaning downward deformation, exceeds 5% of the initial height. The results are reported as the temperatures at which deformation reaches specific thresholds. These are recorded as T0.5, T1, T2, and T5, corresponding to deformation levels of 0.5%, 1%, 2%, and 5% of the initial height. This method provides a much clearer picture of how the material deforms progressively as temperature rises. And that information is crucial for preventing furnace deformation and damage in real service conditions. Now let us talk about erosion resistance, a property that is absolutely critical in environments where refractory faces high-velocity particle streams. Think of your fluid catalytic cracking units, blast furnaces, cyclone separators, and similar equipment. To measure this property, we use the ASTM C740 test method, which simulates an erosive environment. Here is how the test works. An abrasive medium of 1000 grams of size-graded silicon carbide grain is used as the erosive agent. This silicon carbide is blasted through a nozzle, using compressed air at 65 pounds per square inch pressure, directly onto the refractory surface. The test sample itself measures 115 by 115 by 25 millimeters. Before testing, the samples are fired at 815 degrees Celsius to replicate their service condition. During the test, the volume of material abraded away, measured in cubic centimeters, is recorded as the erosion loss. Why does this matter? Because in refinery operations, a refractory with poor erosion resistance will be quickly worn down in an FCCU or cyclone. That means premature failure, equipment damage, and costly downtime. In short, selecting a refractory with high erosion resistance in these applications is not optional. It is non-negotiable for reliable performance. Now let me show you what erosion testing actually looks like in a laboratory setting. The erosion loss testing machine consists of a pressure vessel filled with silicon carbide, a regulated air supply at 65 pounds per square inch, and a nozzle assembly aimed directly at the test surface. The test sample is carefully weighed and positioned at the precise angle and distance from the nozzle. Standardization here is critical, because without it, the results would not be reproducible. After the erosion exposure, which continues for a defined duration until enough material loss occurs, the sample is weighed again, and the volume loss is calculated from the mass difference. In the photograph, you can see a sample after erosion exposure. Notice the characteristic pitted, rough surface where silicon carbide particles have impacted and abraded the refractory. This visual comparison between a fresh sample and an eroded one gives experienced engineers immediate insight into material performance under abrasive conditions. Now let us discuss thermal conductivity, one of the most important properties in refinery heat management. Thermal conductivity measures the rate at which heat transfers across a refractory surface, and it is expressed in watts per meter Kelvin. Why does this matter? In insulation applications, low thermal conductivity keeps heat inside the furnace, which means better fuel efficiency. In refractory walls of hot equipment such as boilers, thermal conductivity affects the cold phase temperature, and that directly impacts the design of downstream equipment. There are several test methods used to measure thermal conductivity. The Indian standard IS 3345, known as the guarded hot plate method, measures heat flux across a controlled temperature difference. The ISO 2477 hot wire method uses a heated wire, where the temperature rise indicates conductivity. And the Indian standard IS 9490 water calorimeter method measures heat absorbed in cooling water. From a practical perspective, dense refractories typically have thermal conductivity between 1 and 5 watts per meter Kelvin. Insulating refractories can be as low as 0.2 to 0.5 watts per meter Kelvin. And fiber-based insulation may be only 0.1 watts per meter Kelvin, or even lower. Understanding the thermal conductivity of your chosen material is essential for calculating furnace wall thickness, insulation requirements, and operating costs. In short, it is a property that directly connects material science to energy efficiency and system design. Now let us talk about permanent linear change, often abbreviated as PLC. This property is absolutely critical because it tells you how the dimensions of a refractory brick will change when exposed to real working conditions. The physical reality is that most refractory bricks expand when heated. There is one exception: soft-fired magnesite bricks actually shrink. But expansion is the norm. Understanding PLC is essential for designing furnace expansion joints, because if expansion is not accounted for, the refractory lining can buckle, crack, or spall. Different test standards define how PLC is measured. The ASTM method uses a standard brick of 9 by 4.5 by 3 inches. The specimen is heated according to a schedule defined by brick type. The temperature is held at the test value, then cooled, and the size is measured again at room temperature to record any permanent dimensional change. The British Standard Method is essentially identical to the ASTM procedure. The Indian Standard Method specifies a specimen of 50 by 50 by 125 mm. The specimen is heated according to the Indian Standard Schedule, and changes in both length and volume are reported. The ISO method uses rectangular prisms of 50 by 50 by 60 mm, or cylinders of 50 mm diameter and 60 mm length. The specimen is heated according to the test temperature specifications. The temperature is held for 5 hours, then cooled, and any permanent dimensional change is recorded. Why do these differences matter? Because each standard uses different heating rates and hold times, and that directly affects how the material reacts. This is why it is essential to always specify which standards PLC values you are using when comparing materials. In short, PLC testing ensures that engineers can design furnace linings that safely accommodate expansion and avoid costly failures. One of the most destructive phenomena in refractories is thermal spalling, caused by thermal shock. Here is what happens. When one surface of a refractory brick is suddenly exposed to a much higher temperature than the rest of the brick, that hot surface expands rapidly. The cooler interior does not expand at the same rate, and this mismatch creates internal tensile stresses that literally tear the outer surface apart. The result is a rough, fractured surface around the grains, a classic sign of thermal shock failure. And this is not just cosmetic damage. Thermal spalling can destroy a refractory lining in days if the material cannot withstand repeated thermal shock. Now let us look at the British Standard Method for testing thermal shock resistance. This test is designed to mimic the real stress a refractory faces inside a furnace. Imagine this: 3 prism-shaped specimens, each standing about 3 inches tall with a 2-inch square base, are placed carefully inside a cold furnace. The furnace begins to heat, slowly and steadily, until the specimens reach the test temperature over the course of 3 hours. Once they are hot, the temperature is held for half an hour, giving the bricks time to soak in the heat. Then comes the shock. The specimens are pulled out of the furnace and left to cool in open air for 10 minutes. After cooling, they are placed back into the furnace, and the cycle begins again: heat, hold, remove, cool, repeat. After each cycle, the specimens are inspected. Engineers look closely for cracks, chipped corners, or any signs of weakness. Sometimes they will even pull on the specimen by hand or with a rig to check its strength. The test continues until the specimen finally gives way, when it can be broken apart by hand. That moment marks the end of the test. The report records the test temperature, the number of heating and cooling cycles the specimen survived, and the exact cycle when cracks first appeared. In short, thermal shock testing tells us whether a refractory can survive the rapid temperature changes that are common in real furnace operations. Now let us examine the ASTM method, a different approach to thermal shock testing. In this method, a standard brick about 9 by 4 by 3 inches in size is selected as the test specimen. Before the actual shock test begins, the brick goes through a preheating furnace treatment. This step is critical because it reveals whether the brick tends to fuse or vitrify, whether it swells or shrinks, and whether it suffers from structural spalling simply from heating alone. Once preheating is complete, the real thermal shock test begins. The brick panel is quickly heated to a specified temperature within just a few minutes. And then, without warning, it faces rapid cooling, a blast of compressed air, or sometimes a spray of water, depending on the test variant. This sudden change creates a far more dramatic thermal shock than the slower cycles used in the British Standard method. After the test, reporting is detailed. First comes visual documentation, photographs of the brick after preheating, notes on its condition, and measurements of spalling loss in terms of volume. Then comes crack analysis. If cracks are not obvious in the photographs, they are described carefully. Often, engineers will turn the spalled bricks on edge and take another photograph to highlight the characteristic crack patterns that reveal the direction of thermal stresses. And here is why this matters. Those crack patterns are diagnostic. An experienced engineer can look at how the cracks propagated and immediately understand the stress distribution, whether the failure was uniform across the brick or localized to a weak zone. In short, the ASTM method does not just measure resistance. It tells the story of how a refractory responds to sudden, violent temperature changes, giving engineers the insight they need to design linings that survive real furnace conditions. Let me clarify an important distinction. We have already talked about permanent linear change, or PLC. Now it is time to look at something different, reversible thermal expansion. Think of it this way. When a refractory brick is heated, it expands. But unlike PLC, this expansion is not permanent. As the brick cools back down, it shrinks right back to its original dimensions. That is why we call it reversible. It comes and goes with temperature. Why does this matter? Because in a furnace lining, bricks are constantly expanding and contracting with every heat cycle. If proper expansion joints are not designed, the bricks will press against each other, creating compressive stress. The result is spalling, cracking, and premature failure. To measure reversible thermal expansion, engineers use the dilatometric method, which is essentially a precise measurement of how the specimen's dimensions change as the temperature rises and falls. Different standards define how this test is carried out. The Indian Standard 1528 Part 19 and the British Standard 190 to Section 5.3 specify the temperature ranges, the heating and cooling rates, and how dimensional changes are recorded. From a practical perspective, most dense refractories show reversible expansion in the range of 0.3 to 0.8% over their working temperature. Insulating materials, because of their porous structure, often show higher percentages. So in short, reversible thermal expansion is the property that tells us how much a refractory will breathe with heat cycles. And it is the engineer's job to design joints and linings that can accommodate that breathing without breaking. There is one very important property of refractories: resistance to the disintegrating effect of carbon monoxide. In certain refinery environments, especially in atmospheres rich in carbon monoxide, such as blast furnaces or reduction processes, carbon monoxide resistance becomes critical. Why? Because carbon monoxide has a unique and destructive effect on some refractories. It does not simply oxidize the surface. It can actually break down the internal structure of the material. The test procedure for carbon monoxide resistance is very specific. Cylindrical specimens are prepared, each measuring 50 mm in height and 30 mm in diameter, or any convenient shape of similar volume. These specimens are then placed in a furnace and exposed to a continuous stream of carbon monoxide gas. The temperature is maintained between 450 and 500 degrees Celsius, and the exposure continues for 100 hours, or until the specimen completely disintegrates, whichever comes first. During the test, engineers carefully observe the specimens. They look for carbon deposition on the surface, often seen as a black coating. They record the degree of disintegration or material loss, and they note any structural changes visible in the refractory. The practical implication is straightforward. If a refractory shows significant disintegration in this test, it is unsuitable for carbon monoxide-rich environments. In such cases, engineers must specify materials with proven resistance, typically magnesia-based refractories or specialized neutral refractories. This test is also highly relevant in hydrogen reformers, which operate in reducing atmospheres rich in hydrogen rather than carbon monoxide, and in partial oxidation units. Understanding resistance to carbon monoxide and hydrogen is non-negotiable for reliable performance in these applications. Now let us examine gas permeability, a property that tells us how easily gases or liquids can pass through a refractory material. This is especially important when dealing with porous or fibrous products. Think of it as measuring the breathing ability of the material. The test records the volume of gas or liquid that passes through a specimen at room temperature, under a specified pressure difference. In the ISO method for gas permeability, the procedure begins with a specimen shaped as a cylinder, 50 mm in diameter and 50 mm in height. A stream of dry gas is passed through the specimen, and the pressure drop across the material is carefully recorded. This is not done just once. Measurements are repeated at least 3 different flow rates. Using the geometry of the specimen, its thickness, and the pressure drops at various flow rates, engineers calculate the permeability coefficient. Why does this matter? Because permeability has very different implications depending on the type of refractory. In fibrous insulation products, high permeability is expected and acceptable. In dense refractory brick, permeability should be low to prevent unwanted gas penetration. And in specialized applications, such as air slide systems or gas-permeable refractories designed for thermal management, controlled permeability is actually desirable. The real-world connection is simple. If you are using porous refractories where gas leakage must be prevented, you need to know and control the permeability. On the other hand, if you are using fiber insulation, understanding its permeability helps you anticipate possible air infiltration paths. In short, gas permeability testing ensures that the refractory material performs exactly as intended, whether that means blocking gases, allowing controlled flow, or managing heat transfer in demanding industrial environments. Now we shift our focus to properties specific to ceramic fiber insulation products, materials that are increasingly used in refinery applications. One of the most critical properties here is the mean fiber diameter. This tells us the average thickness of the individual fibers that make up a fiber blanket or module. To measure mean fiber diameter, engineers use optical microscopy to view the fibers under magnification. Photographs are taken of the fiber structure, and then the diameters of many individual fibers, often more than 100, are measured. From these measurements, the arithmetic average is calculated, and that becomes the mean fiber diameter. To ensure accuracy, only particles with a length-to-diameter ratio greater than 2 are counted. This excludes short and guarantees that the measurement reflects actual fibers, not impurities. Why does this matter? Because fiber diameter influences several key performance factors. Smaller fiber diameter means higher surface area, which improves insulation efficiency. Fiber diameter directly affects thermal conductivity. Finer fibers usually provide better insulation. Fiber diameter also impacts maximum use temperature. Finer fibers tend to have lower refractory limits. And fiber diameter influences vibration resistance and fiber loss during operation. When ordering ceramic fiber products, you will see the mean fiber diameter specified in micrometers. For modern high-performance fibers, this typically ranges from 3 to 6 micrometers. In short, mean fiber diameter is not just a number on a specification sheet. It is a property that determines how well ceramic fiber insulation will perform in real refinery conditions. Closely related to fiber diameter, there is another important property of ceramic fiber insulation products, called short content. So what exactly is short? Short refers to the granular or particulate non-fibrous material that ends up inside the fiber blanket or module. During manufacturing, not all fibers form correctly. Some remain as small, hard particles, and these are the short. Why does this matter? Because high short content can significantly reduce the thermal performance of the insulation. More short means fewer effective fibers doing the job. Short also makes the product harder and less compressible. It increases thermal conductivity since short conducts heat better than the air-filled fiber spaces. And it creates weak points in the structure. To measure short content, engineers use the ASTM C892 test method. A sample of ceramic fiber material is taken and passed through 3 sieves with defined openings. The particles retained on each sieve are weighed. This is the short. The total specimen weight is also measured, and the percentage of short is calculated by dividing the short weight by the total weight and multiplying by 100. What do the numbers tell us? Modern, high-quality fiber blankets usually specify short content of less than 5 to 8% by weight. Anything above 10% is considered excessive and will negatively affect insulation performance. Here is a practical tip. When comparing ceramic fiber insulation products, always check the short content specification. It is a key quality indicator that goes beyond price and directly impacts how well the insulation will perform in service. Now let us move to another important property of ceramic fiber materials, called linear shrinkage. This is different from the permanent linear change we discussed earlier for shaped refractory bricks. So what exactly is being measured? Linear shrinkage records the permanent dimensional change that occurs in fiber materials when they are exposed to extended high-temperature conditions. Why the emphasis on fiber materials? Because fibers behave differently than dense bricks. They are more prone to microsintering and phase changes, and these processes can cause the fibers to shrink over time. To measure this property, engineers use the ASTM C356 test method. A specimen of ceramic fiber blanket or board is carefully measured at room temperature. It is then heated to a specified temperature, depending on the fiber type and its rated use temperature. The specimen is soaked at that temperature for a defined duration, typically 24 hours, before being cooled back to room temperature. The dimensions are measured again, and the linear shrinkage percentage is calculated by comparing the original and final measurements. What do the results tell us? High-quality modern fiber blankets usually show 0 to 3% shrinkage. Anything higher can signal potential service issues because the fiber will compress over time, reducing insulation thickness. And here is the critical point. You must know the shrinkage value at your specific operating temperature, not just at a standard test temperature. For example, if you specify a 100 mm thick fiber blanket, but it shrinks by 2% at your operating temperature, you are losing insulation thickness and effectiveness. That reduction must be factored into furnace, wall design, and efficiency calculations. In short, linear shrinkage testing ensures that ceramic fiber insulation will maintain its thickness and performance over time, even under the demanding heat cycles of refinery operations. Now let us discuss tensile strength for ceramic fiber materials, the final fiber-specific property on our slide. Tensile strength measures the ability of a fiber material to resist pulling or parting forces. This is very different from compressive strength. Instead of testing how much the material can withstand being crushed, we are testing how much it can resist being pulled apart. Why does this matter for fiber products? Because fiber blankets experience tensile stresses in several ways. When they are installed on curved furnace walls, they are stretched and pulled. During operation, vibration creates cyclic tensile stresses. Thermal cycling adds another layer of stress, as different parts of the material expand at different rates. The overall integrity of the fiber blanket depends on its ability to maintain tensile strength under these conditions. To measure this property, engineers use the BS 1902 Part 6 test method. A specimen of fiber blanket is prepared, usually cut into a strip of defined dimensions. It is mounted in a tensile testing machine, which applies a controlled pulling force. The load is gradually increased until the specimen either breaks or deforms significantly. The maximum load before failure is recorded. From this, the tensile strength is calculated using the formula tensile strength equals maximum parting force divided by width multiplied by initial thickness. The result is expressed in pascals or sometimes in kilograms per square centimeter, depending on the standard convention. In context, ceramic fiber tensile strength is low compared to dense refractories, typically in the range of 0.1 to 0.5 megapascals. This reflects the nature of fibrous materials. Their strength comes not from individual fibers, but from the way the fibers interlock and support each other as a system. Here is a practical consideration: always verify tensile strength specifications when procuring ceramic fiber blankets. It is a direct indicator of how robust the product will be during handling, installation, and service. Congratulations! You have completed episode 3 of RefineryPro, Understanding Refractory Properties. By now, you have a strong grasp of the three major categories of refractory properties. First, the general properties such as density, porosity, strength, and composition. Second, the high-temperature properties that reveal how materials actually perform in service. And third, the special properties that address unique operating challenges. You have learned the importance of test standards, ASTM, ISO, and Indian standards, and why specifying the standard matters, since results can differ. You now understand density and porosity trade-offs, why cold crushing strength has limitations, and why modulus of rupture is significant. You have seen how refractoriness under load defines real operating performance, and why erosion resistance is non-negotiable for certain equipment. You have explored thermal properties, conductivity, expansion, and shock resistance, and how these directly influence furnace design and operational efficiency. And for modern fiber insulation, you now know the meaning of mean fiber diameter, short content, linear shrinkage, and tensile strength, and why each of these properties is critical for your application. In our next episode, we will bring all of this knowledge together. We will explore refractory selection and application, how to use these properties to choose the right material for your specific equipment and your refinery. If you have found this series helpful, do not forget to subscribe to Refinery Pro and share this episode with colleagues and peers in the industry, especially those involved in refractory selection and maintenance. Thank you for investing your time in technical learning. This commitment is what keeps refinery operations running at excellence. Stay connected. The best is yet to come.